Okay, so for 11.2, I'm actually going to break this into two different videos because they're very, very similar, but they're also a little bit different. So for 11.2a, same thing as before, we're going to be doing tests with tables. This one's called tests for homogeneity, and it's going to be very, very similar to the goodness of fit test. The issue is, or the difference is, not the issue, the difference is that we will be working with two different populations here, where with goodness of fit, you only had one population and multiple things that you wanted to know about the population. So for instance, the M&M activity was, our population was M&Ms, then we wanted to know the color distribution. For tests of homogeneity, we want to know if there's a difference between two different or more, several different populations here. So here are your hypothesis or hypothesi that there is no difference in the distribution of categorical variables. And then there is a difference. So very, very similar to the chi-squared null and alternative hypothesis. There is a difference. There isn't a difference, and there is a difference. When you have your test for homogeneity, you still have your same conditions as before, your random, your 10%, and your large counts. And I'm going to highly recommend that you get very, very good at sheets where you can figure out what these large counts are. And you'll see why today, but other than that, nothing changes. When you're finding your expected counts, so the first video, 11.1, you had a certain percentage, and then we multiplied each one of the values by that percentage. And sometimes you're given that, but sometimes you want to figure out what your expected is by using this formula right here. It's row total times column total divided by table total. And basically, it's finding the probability that something exists and then multiplying it by the number that's in the cell. So it's all based off of probabilities. If you want to know why that actually works, why this formula works, let me know. But I'm guessing probably at this point in the course, most of you are ready to just know the formulas. And there it is, row total times column total divided by total total. And then your degrees of freedom slightly different this time, and that's going to be number of rows minus 1 times the number of columns minus 1. And again, we'll get practice with that in just a moment. And last but not least, the chi-squared statistic does not change from before. So it's the observed minus the expected squared over the expected, and then you add them all up. The only thing that does change, as I just said, the degrees of freedom of number of rows minus 1 and then times the number of columns minus 1. Your p-value does not change from goodness of fit. Remember, it's only to the right. So it's always going to be your chi-squared to 10,000 and then your degrees of freedom. Okay, just in case you want it, your reference paper should be handy. So this would be over here on I think it's the front of the second page. And again, I'm down here in this distribution of categorical variables. Last time we talked about goodness of fit, that's this one right here. So this one has 2 or more samples, and you'll see an example of that in just a moment. It is a test. Here's the name of the test. Here's your chi-squared statistic. Degrees of freedom, we just talked about that. And then your conditions are right over there to the side. So we're going to go ahead and just do an example, and then we'll practice this more in class. So for this question here, it wants to know if the distribution of birthdays has changed since the, since planned C-sections became more common. So they want to know whether maybe doctors would schedule C-sections during the week so they wouldn't have to do them on the weekend. So did that decrease or increase the amount of C-sections on certain days? So we have two different populations here. So it should be very, very obvious that we have two different populations. We have a population of babies that were born before 1980, and then we have a population of babies that were born after 1993. So very, very different, distinct populations. And then about each one of them, we want to know about the day of the week. And we want to know, is it the same? They're the same number of babies born on Sundays and then Mondays and then Tuesdays between those two distributions right there. Okay, so you can read through this. There's our sentence. Is there convincing evidence that the distribution of birthdays has changed? It usually says, do these data, whatever. Okay, so for state, For state, I put in there, we wish to test the following hypothesis at alpha equals 0.05. Your null is that there is no difference in the distribution of birthdays for babies born before 1980 and babies born after 1993. And then your alternative is that there is a difference in the distribution. So you can see here it is in context. This is my no difference. This is my difference. For plan, there's the name of the test. We will use a chi-square test for homogeneity of proportions. It's right there on the reference paper. Random sample of people from each age group. 10%, I multiplied 10 times each one of these totals right here. So that gave me 770 and 730 people born before 1980 and after 1993, respectively. Now, to do large counts, we need to check to see if all expected counts are at least 5. Now, if you remember, to find your expected counts, you're going to do row total times column total divided by the table total. So I went over into a Google Sheets, and this is going to be the easiest place to do this. And I am going to copy this table, not including the totals because I don't need them. I'm going to put that right over here so I have my expected. I'm going to delete out these numbers right here because these ones over here are my observed. This is what actually happened. And then these over here are what we expect to happen. So my observed minus my expected. Okay, so now how do we find these? We're going to do a formula. So the formula says you equal your row total. So I'm going to come over here to my row total for Sunday. That's 21 times my column total. So go across to 21, go down to 77 and just click. And then I want to divide that by the table total, which is 150. And then you click enter and it tells me that I would expect the number of births, I'm probably in like millions or something. In my sample, sorry, to be 10.78. And again, we could do the same thing with the next one. And we would say equals your row total times your column total, and then divide that by the table total to get those expected counts there. Okay, now this gets a little bit tedious and you're like, oh, it's Excel. There's got to be an easier way. And there is. So right now, I would like to be able to just drag down. But if I drag down that box right there, what it does is it gives me errors because it's changing. So if you look here, it's changing this to be D11. Well, there's nothing in D11 because it shifts everything down. That's what that does. So what I want to be able to do is there's certain things in this formula that I want to keep. For instance, for this whole column right here, I want that 77 to stay constant. I don't want that to change. So what we do to keep things to stay is we use an absolute reference, and all you do is you just add dollar signs in on either side of the B. Now, I also want that 150 to stay. That's not going to change. So I'm going to, again, put dollar signs around the D. So anytime you want an absolute reference, meaning I don't want those numbers to change, you put dollar signs around the letter. Okay, now watch what happens when I drag down with any luck. It keeps that absolute reference. So if you look at all of these, the D10 stays and the B10 stays. What is changing every time is the row total. So the row total is corresponding to the 4th row, and then the 5th row, and the 6th row, and the 7th row, and the 8th row, and so forth. Okay, now we're going to do the same thing on the other side so that we can get those totals pretty quickly. So remember, I want the column total to stay because that's going to stay constant. And I want the table total to stay. That's going to stay constant as well. Click enter. And then when I drag down, I will get all those values there. Okay, so now we did that to find our expected values. Again, you can do that by hand. If nothing I just said makes sense, do it by hand. That's fine too. So that gave me all of those expected values, and they are all at least 5. So that meets that large counts condition because all expected counts are at least 5. Okay, you need to show that work at some point too. You can't just leave it. But anyways, do, for the do, this is the chi-squared statistics. So we do the observed minus the expected squared and then over the expected. You must show work. So if you look here, I put in a couple of examples. So how did I get those examples? I went to my spreadsheet and I said, okay, this one corresponds with this one. So Sunday before 1980 to Sunday before 1980. So I did 12 minus 10.78. And then I squared that, and then I divided it by 10.78, which is my expected. And then I did that again. So then I went over here and I said, okay, now let's go to this one. So 9 and 10.22. So then I did 9 minus 10.22 squared, and then divided that by the 10.22. And then I did do one more just so they could see what happens next. I went down here and I did 12 to 11.81. 12 minus 11.81 squared, and then divided that by the 11.81 plus ... because that gives the reader enough information to know that I know what I am doing here. Now, what I need to do is the formula. The easiest way to do the formula is I'm going to make 2 rows. These are all my expected, and these will be my observed. Now, I'm just going to take them out of the table. There might be a different way to do this, but I think this is the easiest. I'm going to control paste, and I'm going to put the 9 right after that 11 right there. So all I did was I did all of the before 1980s, and then I followed that with all of the after 1993s. Okay, now I'm going to put in my observed. Now this one is tricky. So if you're like, oh, this is so easy, I'm tuning her out, tune me back in right now, because when I copy and paste these over, remember, those are formulas right now. I don't want to bring over the formula. I only want to bring over the number. So instead of doing Control V, I'm going to right click and go paste special, and make sure you only paste the values. Clearly, I forgot to copy it. Hold on. Do this. Go Control C. Now right click and then paste special and values only. And that will just bring over the values and not the formulas. We do not want the formulas. We just want the values. And clearly, I just did not take my advice. Right click, paste special, values only. Okay, so now you can look here and you can just go down. Just make sure they correspond. So for instance, like this 17 right here. So 17 over here was Thursday after 1993. Thursday after 1993 should be 11.68. So you can see that they are still lined up. They do need to correspond. Okay, now I'm going to put in my formula. So this is my chi-square equals parenthesis your observed. Did I missed those? I'm sorry. This is my observed. These are my expected. Equals, sorry about that, observed minus expected. And I want to square that, and I want to divide that by the expected amount. Okay, so I'm going to take that, and then now I do not need that absolute reference because I want that to work down the list every time. And then to find my chi-squared, I need to sum that up. So I'm going to sum up all of those numbers, and that gives me 6.55. That is my chi-squared value. So that's that value that went right there. So then let me just recap really quick so you know how I did that. The first thing I did was I calculated my expecteds by using that absolute cell reference. And then I copied and pasted each one of the cells over here. Make sure you use a paste values only. Then I'm going to use the formula for chi-squared, which is on your reference paper. Observed minus expected squared divided by expected. And then I summed up all of those chi-squareds to get that 6.55. Oh, that should be chi-squared. Yeah, that didn't copy over correctly. So this right here should say chi-squared CDF is equal to 6.55 to 10,000. Okay, now how to find the degrees of freedom. For your degrees of freedom, it's the number of rows. So we've got two columns, it doesn't matter, minus 1 times the number of rows, which is 7 minus 1, which would give me 1 times 6, which is equal to 6. So that's where I got my degrees of freedom from. Conclude, since P is greater than alpha, because I got that P value there of 0.3645, we fail to reject the null. Therefore, we do not have convincing evidence that there is a difference in the birthdays for the babies born before 1980 and 1993. So we failed to reject, so therefore we do not have evidence of a difference. Okay, so what has changed today? Today, pretty much the only thing that changed was that we had to find those expected values by doing row total times column total divided by total total. Everything else stayed the same as it did the day before. So consult your reference paper. We'll get some practice, and hopefully You'll be pretty confident with this.